Section 12.5, volume thermal expansion. So not only do we have a change in length, but it's going to happen, as I mentioned in the last example, in all directions. So we have a volume thermal expansion. The volume of an object will change when its temperature changes. So the change in volume is equal to beta, the coefficient of volume expansion, times the original volume times delta T, the change in temperature. This equation's basically identical to what we had for the linear thermal expansion, but now we're dealing with a volume instead of a linear case, and we have a slightly different coefficient. So the common unit is still the same, of being inverse Celsius degrees, but the beta is something we'll have to get from that table, but from the next column over. Let's look at an example of this in practice. So an automobile radiator. A small plastic container called the coolant reservoir captures the radiator fluid that overflows when an automobile engine becomes hot. The radiator is made of copper and the coolant has an expansion coefficient of 4 times 10 to the minus 4 inverse Celsius degrees. If the radiator is filled to its 15 quart capacity when the engine is cold, 6 degrees Celsius, how much overflow will spill into the reservoir when the coolant reaches its operating temperature, 92 degrees Celsius? All right. So first off, taking a look at the picture they have, we're actually focused on the radiator, which we can't see much of because it looks like a radiator. And then we know the overflow will go to the coolant reservoir. So there's somewhere for this to go, which is good. But I might redraw in my radiator and then make it three-dimensional since it mentions a volume. Okay, so there we have the actual radiator itself, which is great. And then we could fill in the coolant, right? Coolant. Awesome. So we know the coolant entirely fills the radiator. That tells us something, right? There's this 15 quart capacity. Quart is a unit of volume. It's not our SI unit, it's not cubic meters, but it is a volume unit. And since the problem doesn't specify the units that it wants for the overflow in a change in volume, we can work in terms of quarts. So our original volume is going to be this 15 quarts. And we want to find, as I mentioned, how much overflow. So the how much there is the volume of coolant that we lose. So delta V overflow. Great. So we have that. Is there anything else that we know here? Well, we do know the change in temperature, right? We know we're going from 6 degrees Celsius to 92 degrees Celsius. So our delta T is going to be the final 92 minus the initial 6, and that will be in units of Celsius degrees. So 86 degrees, 86 Celsius degrees. Great. So we have that. Anything else that we have here? They mentioned the coolant has an expansion coefficient of 4 times 10 to the minus 4 Celsius degrees inverse. And since it's liquid, we already know that that's going to have to be the beta value. We don't have a linear version for liquids. So that's going to be our beta. Great. Anything else? There's a couple other things. We can note that some materials are mentioned, right? They mentioned that there's a plastic container for the reservoir, and the radiator is made of copper. So anytime a material is mentioned, we want to hone into that to check if that's a clue. Here we're focused on the coolant in the radiator, so I'm going to really focus on copper specifically. Why might I care about the copper? Well, the coolant is going through this temperature change, so it's going to expand. The copper is too. The radiator that's holding the coolant, the container, is going to get bigger as well. And to be fair, the small plastic container of the coolant reservoir will also expand. We don't really care how much that expands by because that's just going to catch however much we have. We haven't been given any constraints on that. So copper is something that we can look up what its thermal expansion coefficient is for a volume change. So let's take a look and see if we have copper in that table. Oh, we do. Copper is the fourth one down. Volume is here, 51 times 10 to the minus 6 inverse Celsius degrees. All right. So this is looking pretty good. One other thing that we can note, actually, just while we're looking at this chart, is that the volume coefficients for metals, ones where we have a linear one, are just going to be 3 times the linear one. That you could think of a cube. If you have a cube and you expand it by length, by width, and by height in each of those directions, that's a factor of 3 possible directions to expand. So the volume coefficient is 3 times that. So I just want to mention that if you have 12 times 10 to the minus 6, it becomes 36 times 10 to the minus 6. It's not something essential to know because this table would be given to you, but it's just a useful little tidbit. All right, so if we go back to calculating the change in volume, we want to calculate it for the radiator, for the coolant, and figure out how much we are going to lose to the overflow. So we can calculate the change in volume of the coolant with its coefficient of volume thermal expansion times the volume original of 15 quarts times that change in temperature of 86 Celsius degrees. And that comes out to 0.53 quarts, which is pretty big, but we aren't going to lose all of that because the radiator does increase in size. So we can put in that 51 times 10 to the minus 6 inverse Celsius degrees times 15 quarts times the same change in temperature, 86 Celsius degrees. It comes out to 0.066 quarts. The radiator gets a little bit bigger, not by a lot, but a little bit bigger, so we don't lose quite as much coolant to the reservoir. So the delta V, the overflow volume, is going to be how much the coolant increases minus how much the radiator container increases. So it comes out to 0.46 quarts. So this is a useful way to calculate things, and it also can be why they don't always design things to be filled right up to the limit of the max capacity, because once they heat up, they are going to expand. Just things to keep in mind. All right, one other really important application of volume thermal expansion is with water. Water, it turns out, is pretty strange in how it expands, because like most liquids, it does expand as it gets warmer, but as it gets cooler, it only contracts to a point. At 4 degrees Celsius, water reaches its maximum density. That's as much as it contracts. And then if you keep cooling water, it actually starts to expand, right? The density goes down because the volume is going up. It's not a huge effect, but it's significant. This is actually why the ice will form at the top of lakes instead of at the bottom of lakes, because the water becomes colder and colder, and then it sinks down to the bottom at 4 degrees Celsius. But once it gets colder than 4 degrees Celsius, it actually will start, once the whole lake is that cold, the colder water will actually start to rise to the top. It'll float on the more dense water. So the coldest water will reach the surface and form a layer of ice. Once you have that ice there, it actually becomes a nice insulator, so the rest of the water often won't freeze. It can still freeze through. But this is really good for fishes, because if the ice started forming at the bottom, then the whole lake would often freeze, right? The fish would die every year or have to go somewhere else. But as it is, If the ice forms on top, they can still swim around freely underneath. This is not so good for pipes. So if you have a, a pipe that's exposed to the cold outer air, then it's possible for ice to form. And that ice is then going to expand and take up more space. This is fine on the side that connects to the water mains. The water will still be at normal pressure. Where there's a problem is the water that's held between that ice, the frozen part of the pipe, and the closed faucet. Because now, as the volume expands in the ice, that water is at very high pressure and it's got to go somewhere. So, this is where you can get pipes bursting. And it's why, if you live somewhere that's really cold, you often get encouraged to leave the tap dripping. That's a good thing because that prevents your pipes from bursting due to this volume thermal expansion. So, super cool effect. We don't see it very often in most places in California, certainly not Monterey, but good application in case you go to live elsewhere where the temperatures can be a bit more extreme. You will see these effects.